Okay, line R1, we're taking a look at learning task 5, where we are going to go through induction lighting. And induction lighting is a newer technology in all of our lighting technologies that are out there. The concept has been around since the 1800s, but it was not feasible for a long time until, really early 2000s is where we start to see it gain a little bit of a mainstream foothold. That being said, in a lot of ways, it has been surpassed. It's kind of like the 8-track tape. It was a really, really good thing, but it's been passed by the upcoming technology, which was going to be LED. But there are some of these around, and they do kind of fall underneath all of this gas discharge lighting. So we'll just cover, what they are inside of here right now in case you ever run into them. The basic concept that they're going to work off of is just going to be magnetism. We are going to go and have a high frequency magnetic field that we are going to go and create. So over here we see that we have got current. We're going to send that current through these coils, and based upon the direction that that current is going through the coils, and they're showing that it's going to be AC, that is going to go and cause magnetic fields to go and be established either in this direction going north to south or in this direction going north to south, and it's going to be flipping around rapidly back and forth from one side to the other. What happens then is that those magnetic fields will go and move particles. So we are going to go and have mercury vapor that is going to be bonded along with other compounds inside of there so that it's going to be able to be picked up by my magnetic field. And then we're going to go and basically move those mercury particles around rapidly and cause collisions. And when we cause those collisions, once again, we're going to start to go and create that UV radiation, which is then going to go and give us that visible light. The big difference with these and regular fluorescent lights is that in regular fluorescent lights, we had a cathode at either end. Just draw that in there real quick. But we had a cathode at either end that we would heat up to go and emit electrons that we would then send across to an anode at the other end. Then they would flip, and the other side would become the cathode, and the opposite side would become the anode. And so we had this constant back and forth of electrons that we were driving through there. Inside of this, we are going to go and have a pre-ionized type of system. In other words, we are going to have a whole pile of particles that are going to go and have an excess of electrons on them, which means that those electrons are going to be relatively easy just through collisions to be able to become freed. As soon as you have that extra electron, it's far easier to bump it out of the shell than it is to remove it out of a regular one. So we cause those collisions as those electrons get emitted. Ultimately, those electrons are then going to go and make collisions with the actual mercury that we are going to have inside of here. It's another drawing over here. It's not the best drawing, but it works. Those electrons, the charged ones that we're going to have inside of there, what we're referring to as the plasma over here, are going to go and make collision with the mercury. When they make collision with the mercury, we are going to once again emit UV radiation. That UV radiation is then going to go and strike our phosphor that we are going to go and have, or what we refer to as the fluorescent powder, which is this just going to go and shift the frequency, right? Ultraviolet is super high frequency light beyond what we as humans can see, whereas, all the others are going to be lower frequencies that are going to be within our visible light range. So it just shifts the frequency, the phosphor 10 turns it into what we refer to as visible light. Multiple different kinds that are out there. Some of them are going to go and look like this, where it's going to be a bulb, and that bulb is actually going to go and have a tube that's going to be on the inside. They call that part the power coupler. They show another picture inside of here where they've got, once again, that power coupler inside of here. This over here is going to be their high frequency generator. It doesn't have to be a ridiculously high value of voltage, but it does need to be a ridiculously high value of frequency so that we can cause enough collisions that we are going to be able to go and emit the requisite amount of light. This is just the inside of what they had for that same type of light. The other ones that we will see will look very similar to what our circline bulbs look like. If you're familiar with your fluorescence, you should be, well, we just covered this, so you all should be at this point. But we have got a type of fluorescent tube that is a circle. And inside of our actual fluorescence, it's actually cut in half. There's a little plastic coupler over here, and then we go and place, the cathode over here, and we place the other cathode over there, and then we just send electrons through. That's a regular fluorescent. Inside of an induction light, it's a complete tube. It's just a donut-shaped tube that is going to be phosphor-coated on the inside. It is going to go and have a little bit of mercury, a bunch of other small substances inside there that are going to be excitable by the magnetic field. And then all that they do is they then take a sleeve and that sleeve goes around it. And so inside of this sleeve, there's going to be multiple windings of wire, and those windings of wire are then going to get taken out to the actual high-frequency generator that they would connect this to. This, in essence, would go and give us what we saw inside of that first picture. Just imagine this tube now being closed all the way around in on itself so that all of those electrons that are trapped inside there are going to stay inside there and cause collisions. As far as efficacy goes, they're pretty good light, relatively good turnover from my watts into my lumens, 65 to 70. They do have a ridiculously long lifespan of the actual tube. Because if you take a look at the tube, there is no cathode to go and burn out. We have no amalgam that we're trying to go and have. It's already just pre-distributed gases inside there. And if that tube never goes and develops any sort of a crack, you're going to be fine. Those gases can't get out. So the bulbs themselves have got a ridiculously long lifespan that is going to go and be, rated for 100,000 hours or more. Okay, we're just going to write that down there. Now, here's the catch, though. You'll note that the manufacturers are only rating the bulb for 100,000 hours. There is nothing that is being said about the high-frequency generator over here, because the high-frequency generator is the one that's doing all the heavy lifting. The rest of this is just gas and mercury trapped inside of a glass envelope. Of course, that thing should be warranted for, a long, long time. The actual lifespan on these things is hard to say. Just because there was not a ton of them placed out there, we don't have a lot of industry experience to go on to say we know what the lifespan is going to go and be. Some of them have lasted really well. Other ones, the primary point of failure has been inside of that driver. As far as our advantages and disadvantages, the advantage was that ultra long life, once again, for the bulb, not necessarily for the ballast. We have got really good white light capabilities. That's all going to be based upon, obviously, the type of phosphor that we are going to be coating the inside of these with. Low maintenance requirements, once they are put in place, they usually do operate fairly well for a long period of time. And we do not get much of a change in our light output, based upon temperature the way that we do inside of a fluorescent. A fluorescent, when the temperature drops, it has a harder time emitting electrons off the cathodes, which means that then that fluorescent is going to have fewer electrons, which means fewer collisions and means fewer light. These ones, we've just got a trapped gas inside, so it's just going to happen the same, more or less, at all times. They're fairly vibration resistant, low operating temperature, no stroboscopic effect, because the frequencies that they're going to be operating at are going to be in the tens, if not hundreds of thousands of hertz that they're going to be operating in. No noise as well at the actual bulb. Sometimes the high-frequency generators can have a little bit of a buzz to them, but it's almost more of a whine, like that high-pitched noise you get out of a variable frequency drive. They do have some disadvantages: cost, availability of parts, and proprietariness. You can't just grab anybody's bulb. You're going to go and buy Philips bulb if you're using one of their systems, or Lumiled, or whoever it is that you're going to be utilizing. You can only buy theirs from the wholesaler that covers it. And it's going to have special sockets. This one over here has got an actual tube that goes inside. That means that this glass bulb over here, although it clicks in, is going to go and have this, hollow envelope for that rod, the power coupler on the inside, which means that it's just, a completely separate and different type of setup. There is also another one that has not been mentioned, and that one is going to go and be the electronic noise and the harmonics. We as a society have so many electronics that contain what we refer to as switching power supplies. These are going to be semiconductor-driven circuits that are going to be utilized in things like any type of a computer, any power supply for microelectronics, all those little wall warts that you plug in your electronics with, the USB sockets that are built inside of receptacles. All of that stuff starts to go and cause junk on our electrical system. We call it harmonics, or we call it electrical noise. These ones over here have got a ridiculously high value of frequency, which means that they can induce, EG is equal to BLV. They can induce voltages into a lot of surrounding cables or other components. Note that it's off of velocity, and it's the velocity of this, not the flux density, but the rapid back and forth that can really cause a lot of generated problems. If you put these things close to electronic copper conductors, stuff that is going to be your Cat5 cables or telephone cables or things like that, they will go and buzz out. You're just going to go and have so much interference as a result of these things being nearby. So be careful with where you place them. Try to keep those ballasts, and then obviously this cord, because this cord is going to be carrying that high frequency, you want to keep that as short as possible and away from anything that's going to be telecommunications. Applications, these are all going to be for up-high type of lighting where we need bright light and lots of it. They give, roadways, airports, lobbies, security lighting, high bays, things like that. They're always going to be up-high ones, nothing that's going to be down low. They're too expensive to place down near the general public because of the proprietariness of the bulbs and the components and stuff. You just can't afford to have these things in any place where they're going to be, in danger or get smashed or anything like that. All right, that is our induction lighting system. In a nutshell, it's a fluorescent tube that is a continuous loop and has no cathode. And the bulbs last a really long time. The ballast, well, that's to be determined. We will see whether these things are still around in another 10 years or not.